Here's an example of a change management control form. In this particular case, we've got a project at the Irish Embassy. We're going to have some sort of a cultural exchange between us and the Chinese. And originally we were going to have a small Irish dance group, and that's going to be changed to allow for river dancers. And so we identify why we're changing it, what areas are affected, who's going to approve it, who's paying for it, where are we at in the priority, and the sign-offs. So a nice simple process to track this particular request. This last slide is a good example of a change request log where all of the changes for a particular project, whether they've come from a risk event or from a customer request or a project team member request, all those get put into one central location. And we identify things like when the request came through, what the impact is in terms of cost, and whether we've approved it or whether it's still open, or if it's out for quotes or what have you. So this is a good way to track everything that's going on the changes to the project. The risks that we've looked at so far are more the qualitative type of risks. And now we're going to get into a little bit of quantitative analysis of the risk on your schedule. And we'll be taking a look at that when we get into PERT and PERT simulation. Program Evaluation Review Technique and Program Evaluation Review Technique Simulation. Two mouthful technical activities that project managers need to know about. And really it's simple. Well, not so simple. But what it is it is the evaluation of the probabilistic values of activity times, and from the individual activity times and their various values of how long activities will take, we can come up with a probability on our schedule for the overall project. These techniques come from us courtesy of the Department of Defense and the Polaris nuclear submarine projects from the 50s. And if you can envision putting a submarine together is quite an enormous task, and wanting to know when that nuclear submarine will be available to be sent out to sea, probably an important information for world power at that time. So let's take a look at this in more detail. PERT, or Program Evaluation Review Technique, assumes that each activity duration has a range of activity times that follows not quite a normal distribution, but what's called a beta distribution. Yes, you'll need to put on your statistics hats again, and we'll take a look at some stuff, but we'll help you through this. So when we do PERT, we look at 3 time estimates for each activity. The optimistic time, that maybe we get 10% of the time or less. That pessimistic time that pops up maybe 10% of the time or less. And then our most likely time, which will represent the 80% value, if you will. So knowing the weighted average and the variances for each of these activities allow project planners to come up with probabilities of meeting different project durations. And we'll see how that works in the upcoming slides. In the last slide, I mentioned that activity times are represented by a beta distribution. The first curve that you see here labeled activity is just that, a beta distribution for the optimistic times A through the most likely times M, all the way to the extreme pessimistic time B. As you can see from the distribution, there are more chances of the project being late than the project activity being early. At least that's what's supposed to be represented by the distribution of the activity times on both the early side and the late side. Looking at the second curve, and that represents the project total expected time. Once we take individual activities and start summing them up and running our network analysis on all the possibilities of times, what we'll see in our analysis is that we get sort of a normal distribution, about a center, with half of our times being early and half of our times being later than the expected time through the network. We can calculate the activity time by taking the optimistic activity time, that 1 chance in 100 of completing the activity early, the pessimistic activity time, same thing, only the activity being late, and the most likely time. And instead of just averaging the 3 values, we'll do a weighted average to force the data to represent that more than likely we're going to hit that most likely activity time. So we'll put a 4 times factor on that. And so with those 6 time values, we'll average them all together to come up with an expected time for each individual activity given this probabilistic data. What we can also do is determine the standard deviation for each activity, and that's simply the difference between the extremes of the pessimistic time minus the optimistic time divided by the 6 values that we've represented through the average small t, small e. Once we know all the individual standard deviations, we can come up with the standard deviation for the project by summing the squares of all the individual standard deviations. Again, only on the critical paths, as it says in the note there. So we'd only take the critical activities and put those through this analysis. Anything not on the critical path is not part of the program evaluation review technique. After we've determined an expected duration of the project based on the individual expected times for the individual activities, we can actually determine a probability of hitting a certain schedule, T sub s, by taking a look at the expected time for the project, capital T, capital E, and dividing that by the square root of the deviation squared of all the individual activities on the critical path. I know I just said a mouthful in the last few slides, and so let's see if we can follow along in an example. And if you follow this example, it should help you out in the next case. So let's say we got this fairly simple project, 6 activities. Given the optimistic times for the activities, the pessimistic time for the activities, and the most likely times, we can calculate the small t, small e individual activity times. And we can also calculate the deviation squared for each of these times. Simply the b minus a over 6 quantity squared. Since we need those values, it's good to have those in a table. So given the information on the last slide and the particular project network shown here, we can see that if we put our expected times for the individual activities into the project network and run a forward pass on it, we will get an expected time for the overall project of 64 days. You need to run a backwards pass to determine the critical path, and if you did that, you would note that the critical activities are A, B, D, and F. So now we can start answering questions about the probability of getting this project done within a certain amount of time based on the expected time through this network of 64 days. Here's a couple examples of probabilities that you can determine based on this information. In the previous example, we had an expected time of 64 days. We asked the question, what's the probability of the project to be completed before 67 days? So our schedule now that we've asked or said is 67 days. We determined that the expected time is 64 days. We subtract those 2 values and take the square root of the deviation squared on the critical path. And what we'll find out is if we schedule this project for 67 days, we have a 69% likelihood of that happening. You can see that if you schedule this particular project out long enough, you'll have 100% of hitting the schedule. If you remember from your statistics, the z-score that you calculate or can get, and I'll show that on the next slide in a second, the z-score actually represents the area under the curve and also the probability at the same time. So let's just look at the second example. It's not drawn here, but as you might expect, instead of testing about a schedule of 67 days, which is greater than the 64 and therefore has a probability of higher than 50%, imagine if you were looking at a schedule of 60 days and you asked the question, what's the probability of getting this project done early? Again, you have some optimistic times that might force the project to be done early, but what's the probability of that occurring? And according to this analysis, again, just subtracting t sub s minus t sub e, dividing by the square root of the deviation squared, you can see the probability of that particular scenario is 26% probability of getting the project done in 60 days. So let's see where we got these probability values from. In the first case, we got a z-score of 0.5, and in the second case, we got a z-score of 0.6. Looking at the z-scores we got from the previous slide, when we had a z-value of 0.5, you can see that it sits right in between the 0.4 and 0.6 value, so 69% seems about right. In the other example, we had a z-score of negative 0.5, and you can see also from the same table that that falls in about the 29% probability. One thing to notice, when t sub s equals t sub e, when your schedule hits your expected time or what you're trying to test against, notice what the probability is. So the probability is 50% for hitting your expected time. So if your schedule time and your expected time are the same, you'll hit that half the time. I think that's worth noting. So now you wonder why we went through this very technical statistical analysis of a project schedule to get a probability. Well, imagine if you could not just do that once, but do that several times, and maybe during the process change the activity times along the time distribution for each of the individual activities. Well, that's what we get when we do this Monte Carlo technique. So we can actually simulate the project being run in a lot of different ways using a specified distribution of time between optimistic and pessimistic, applying random variables to all the activities, and doing all that good stuff. In the Monte Carlo technique, we're going to take this schedule simulation through the various levels of uncertainty across the times of the individual activities, and from that we'll figure out some interesting information about critical paths, the likelihood of certain paths that are currently not critical becoming critical if times change, and it'll allow us to really do a better job of understanding the total schedule risk and understanding how to plan for how we're going to put resources on it, apply for funding for it, and put our materials and equipment to the best use possible. Using the Monte Carlo technique, we can allow project planners to identify that schedule risk and really understand what's going on in the project and all of its permutations. Let's take a look at an example. If we have a project network, and you'll see that in the upcoming slides, of course, just like we said before, we have the optimistic time, the most likely time, and the pessimistic time. And again, we'll assume that the values for A and B sit at the extremes of our data set, and the most likely time is that midpoint. We can use a lot of different types of time distributions. In the case of the PERT simulation that I've taught you in this chapter, we use A plus 4M plus B over 6, giving us 6 data sets and weighting the most likely time a little heavier. We can have this triangular simulation you see here, where we'll just assume a linear relationship between the values. There's other time simulations that we can use to represent this, and I'll show those on the next slide. Again, here are some other examples. We use the skewed one, which is the upper left-hand corner, most of the time, but in this particular example, we decided to use a normal probability distribution for the 3 times. It's shown in the lower left-hand corner. So using a computer simulation generator, we can calculate the average times for the project, varying the activity times along their distributions, and we repeat this backwards and forward pass, just like you do it by hand. We do this 2,000 times or so we can get some really good data out of it. For example, in the activity above, the first simulation, the duration might be 27, and then it may be 13, and then it may be 18. The 3 key pieces of information that are derived from repeating this process 2,000 times are the probability that which paths show up as being critical, and the probability of a particular activity showing up as critical, along with the average simulated project duration. The two percentages that you get out of this calculation are called the criticality indices. So let's take a look at this project network in more detail. This is a Monte Carlo simulation in which we've run 2,000 different iterations varying the various activities along the triangular distribution that we talked about earlier. We can see here the probability of certain paths becoming critical. The probability of 1468 becoming critical is 50%, 2568 is 33%, and so on. We can also look at the probability of particular activities becoming critical. And also we can calculate the duration time for the project, and we can see the extreme of the ranges. Our T sub B, capital T sub B, is 34.81 days in this simulation. Our likelihood to hit all the time is a 40-day project. Our least likely time period is 30 days, a little over 30 days. So we can get a lot of interesting information, and imagine if we needed to interact with 2,000 or 3,000 different tasks, how important this type of technique might become. Of course, it takes some decent computer power to go ahead and do the calculations as well. The Monte Carlo technique is a very powerful simulation tool. It helps us deal with uncertainty of activity times. It shows us the interaction among the project activities. It highlights some of the potential problems for delays or bottlenecks. It looks at our project schedule and gives us a really good handle on the range of activity times and total length of the activities. It identifies activities that will never or rarely become critical, really important to know which activities you don't have to manage so much. And allows for a probability distribution combination to increase the accuracy and flexibility of your schedules. This concludes this week's asynchronous session on Chapter 7, Risk Management and Program Evaluation Review Technique and Methods. Please move on from this and take a look at the rest of the activities that are required for this week's asynchronous session. Have a good day.